Okay, in this lesson we'll focus on the difference between the PI and PD controller. Okay, first of all we need to give the heading in here, PI and PD comparison. Okay, first of all take the system as GS, it's your plant. Okay, Wn square S square 2 zeta omega n S plus omega n square. This is a second order system, and then apply the PI PD controller. Okay, in the first place, and so the PI controller can be applied. Just remember that adding the P and integral controller coefficients of this term, and so GS must be equalized with what, the K1 times S plus K2 divided by K1 divided by S. Okay, and so the R transfer function is also given with the what, the RS plus minus, it's a unity feedback. Okay, and so the K1 and also K2 divided by S plus plus, and GS can be given, and CS. These are to what, to PI controller structure. Okay, and also we can write that the R minus C, this is the error, okay, times DG times G must be equal to the C from this block diagram. Okay, and so C divided by R can be reorganized in here just like this one, DG times G plus DG times G. Okay, this is what, this is the R transfer function. Okay, so if we put the whole equation into the what, into the place of this term, for example, Gg must be equals to the what, this one, G must be equals to this one, and so the Ts can be derived with the what, with these terms, K1 times S plus K2 divided by K1 divided by S times omega n square divided by S square 2 zeta omega n S plus omega n square. Okay, and also we need to add the 1 K1 S plus K2 divided by K1 divided by S times omega n square divided by S square 2 zeta omega n S plus omega n square. Okay, these are the basic form, and so at the final stage we have the TS just like this one, guys, K1 times omega n square times S plus K2 omega n square, and so S over 3 plus 2 omega n zeta S square plus K1 omega n square plus omega n square S plus K2 omega n square carry square. Okay, and so these are the closed loop transfer function for the second order system in this way. Okay, first of all, just see that we have the S over 3. This, the denominator part, is the what, is the characteristic equation. This is the zeros values, right? And so one may notice that we should say that the K1 and K2 is given in here just like this one, but we cannot update the S square coefficients in here, see, and so it means that we cannot reach the every pole on this system, which means that we can set the what, steady state error up to 0, but we cannot reach the every pole, or we cannot place the desired pole to the what? To the root locus in any way, because in order to do that, we need to change these coefficients also in here. Okay? And so, for the PI results, we can write that. Just see, in the PI, we have this kind of transfer function, just like this one, omega n square. Okay? And so, we can manipulate the final value or steady state in here, because at the last stage, if we assign the s is equal to the 0, we have only these terms, just like this one, and so we updated k2 and or the k2 times omega n square divided by k2 times omega n square always creates the what? The ts going to 0 as 1, which means that if we apply step response, and then we will get the what? The 0 steady state error. And also, we cannot directly update it or place the pole in the root locus. Pole cannot be placed in root locus, but to what? To anywhere, because we cannot update easily the characteristic equation of these terms. We should reach the whole the coefficients of the characteristic equation. Okay? This is the PI results. And also, we can see that we can give the what? The PD controller in here for the comparison. Okay? In the PD controller, for GS is equals to what? The K2 times S plus K1 divided by K2, right? And so our transfer function is the what? This one. It's the block diagram. K1 and K2 times S, right? It's the plus, and GS should also be given in here. CS, it's the unity feedback, and so the TS, just like the closed-loop solution of these terms, can be written as to the what? The K2 times omega n square S plus K1 omega n square, right? And also we have the S square plus K2 omega n square plus 2 zeta omega n S plus K1 omega n square plus omega n square. Okay? This is coming from what? The solution of the closed loop transfer function in the unity feedback characteristics. Okay? But see that in the first place, we can set the what? The zeros at everywhere in these coefficients. But in the PD controller, we have these coefficients. Okay? And so, what's the results of these coefficients? First of all, we can reach everywhere. Everywhere in root locus, right? Because we can update K2, we can update K1, and then we can set the every pole at the what? The root locus in here. But we may have steady state error, because just see that if the S is 0, we have the K1 omega n square and K1 omega n square plus omega n carre n square, right? And so does not equalize to the what? To the 1. Okay? This is the deficiency of the PD controller in that case. Okay? So how we can easily write or obtain these coefficients in the MATLABs? So we can write the var5 PD PI comp. Okay? And so we can delete the whole the terms in here, just like this one, And also we can use the symbolic toolbox in here, S, zeta, omega n, k1 and k2, right? This is the symbolic toolbox. And so for the PI we can write that the GCS can be equals to the k1 times S plus k2 divided by k1 times S, okay? And also GS can be written as the omega n square divided by S square plus 2 zeta times omega n times S plus omega n square, okay? And TS in the closed form we have this nomination GS times GS and plus 1 GSC plus times GS, okay? And pretty collect function gives us the proper way to what these coefficients based on what the S. And so if I run this code, and then we will have our coefficients just like this one, okay? This is the solution for the for this nomination. But I'm sorry, this must be divided by S. Okay, just see that these are the results of the PI controller, and so we can easily obtain the transfer function of the anything based on this symbolic toolbox. And also we can write the PID controller just like this one, the PID, and this is the K2 S plus K1 and K2. It's different, right? And so if I rerun this code, and then we will have these nominations just like this one, just we have written the function of these nominations, okay? But just see that in the closed loop response of the PI, and we can write that is simple. The first of these things is the PI. We can control the steady state error, but we cannot reach the every pole at the characteristic equation. In the PD, we can reach all the poles, but we cannot control the steady state error. And so, in somehow, we need to collect these forms into the one form. How we can do that? We can do these terms x to the PID controller, okay? For the PID controller, we can define the seams as KP, KD, and KI, okay? And so the GS is same with the previous one, but in this case, KP plus KE divided by S plus KD times S. And so we can create the superposition of the KI and KD and KP controller in here, just like this one. And so if I rerun this code, and then we will have this nomination. This is the PID controller structure, but in the control engineering perspective, we just see that in the PID controller, these terms are going to the 0. at S is going to 0. And so this term is also going to 0. And so we have yield with Ki times omega n square divided by Ki times omega n square, okay? And also, if we use the D controller in the PID, and then we can update the S square term in here, the coefficients of this term. And also we can update the S term, the coefficients of the S term. And also we can update the S over 0 term in here. And so we can place the poles at everywhere in the root locus. But also we can provide the steady state error is going to 0 when the time is going to infinity, okay? This is the difference between the PD and PI and PID controller, okay? This is how we should define our proper notation in this domain. And so, how we can conclude these informations in here? First of all, we need to give the section 4 in here, the improving SS and transient response in PID. So, up to now, just in this the summary, we have designed the PD and PID controller for steady state error and transient results, but either the transient PD or the SS error PI can be adjusted in time. We must collect these two forms into the one, okay? And so because either the PD or PI decreases the R performance of the output signals, okay? So in order to prevent this code, in order to prevent both transient or SS error, we write or build the what? These terms. RS plus, we can write the KP in here. We can use the error signal in here. KI divided by S, and also we can use the KD S. We can collect the whole the terms in here, just like this one, and so we can feed the what the input values to the GS, and also we can build the what the output signal in here for the unity feedback with the minus terms, and then this is called the PID controller design. Okay, for a given diagram we can say that for example GS is equals to omega n square divided by s square plus 2 zeta omega n s plus omega n square, just like in the MATLAB symbolic toolbox code. And then the GS, the controller S, can be built with what? The KP, KDS plus KI divided by S. Okay, and so this can be collected in the one form in here, just like this one, the KD S square plus KP KD times S and KI KD divided by S. Okay, this is the R solution for the what, or building the what, the PID controller. This is just reorganizing whole the equation with the basis on the what, the new terms. Okay, just see that we have one coefficient in here, one coefficient and one coefficient, but these two coefficients KP KD KI KD is built with what, with the another term of the what, the controller coefficients. Okay, so the R transfer function, in summary, we have this kind of transfer function: KD S square omega n square plus KP S omega n square plus KI times omega n squares. Okay, and also S over 3 plus KD omega n square plus zeta omega n 2 times S square plus KP times omega n square plus omega n square S and KI omega n square. Okay, just see that we have the 0 steady state error, and also we can reach the whole coefficients of these terms. We can set the any other way with what the KI, KP and KD in order to what? In order to satisfy the transient response properties or the steady state response properties. In that case, because we can reach the every pole in the geometric form, we can set the any pole to the what? To the root locus in these utilizations. Okay, in the S-plane we can reach the every point and we can manipulate it. Okay, in the next lesson we will create an example of the what of the PID controller. Okay, guys?